seen something like this before? Anyone have? Hey, class has started. We're having a video. Taking notes? Now, what is that thing up there? Anybody have any idea? It's pretty. Is it like a piece of artwork? No, nobody. Okay. We're going to find out what this is. This is not. This is not somebody's artwork. This is natural. This is part of the abstract world. There's no ooh. Well, yeah. Okay. So everybody here has their exam back, right? If you have questions about your exam, I'm going to kind of leave that. Either you can get me after class or plus hours or something. All right. What is this? Well, we're gonna pause this for the moment. Maybe we'll come back to this. Need a little. Topic for today is section 9-6 in the book. And the topic is imaginary numbers, or probably in the book, I don't know if it's called imaginary or maybe also complex numbers. I don't know how good your memories are, but I can remember when I was in grammar school, and so I had learned about numbers. At some point, they came along and they told me, well, there's like a negative number, -2, -5. But that's weird. Those aren't real. You can't have less than something, right? I mean, that was my gut feeling about it. It didn't make any sense. I mean, I could do the math. They gave me some rules, and like -2 plus 2 is 0, and like 5 plus -2 is like 5 minus 2. There's some rules, but it took me like years and years and years to realize that I had made a mistake. It wasn't that these are negative numbers make no sense or aren't real. These numbers aren't real either. I mean, you can't, like, you can find things in the room that there's one of, but there's no one in the room. It's not a thing. It's an idea. It's an abstract idea. Now, pink elephants are an abstract idea too. Right? But they're not that useful. These are useful. That's why we have them. That's why we learn about them. And it turns out that the negative numbers were useful too. Like, if I have a bank account and I have $1,000 in it, but I also have a loan, for $200, it's useful to think of this as a negative number, because I can add these two and see how much money I really have, right? So these are abstract concepts. Now, I bring this up because we're going to talk about something. We're going to talk about imaginary numbers, and really, there's only one imaginary number you have to really kind of bring into your heart, feel it, and see how weird it is, but figure out how to use it. And that's the square root of -1. You say to yourself, doesn't make sense. I mean, when I first ran into -2, it didn't make sense. How can you have the square root of a negative number? You take two numbers, if x is positive, you get a positive number. If x is negative, you also get a positive number. So with regular numbers, you don't get this. And that's why they're a special category of numbers. Now, okay, I can have pink elephant numbers too, and they're not very useful. Well, these don't seem immediately very useful either. We're going to see a couple uses for them. You just have to take it on faith for the moment that they're useful. Now, before we're done, I will show you why they're useful. It turns out they're very important to the world. They're not just some toy mathematicians made up to play with. They actually have a lot of use. So. Okay, that's my intro. So before I go on, I'm just going to give you some basics. We have a name for the square root of -1. We call it I. We use the letter I. And the basic thing you have to know about I is that I times I equals -1. As counterintuitive as that is, that's really the most important thing. You can think of it as like a game at first, and this is part of the rules we're going to play, but you just have to go with it for a little while. I want you to notice something too. We have I, and we can use I with our other numbers. We can multiply I times -1. We just write it minus I. If I multiply -I times -I, well, that's -1 times I times -1 times I, which is -1 times -1 times I times I. The -1's, -1 times -1 is 1, and I times I is -1 equals -1. So just like I times I is -1, negative I times negative I is also -1. Okay, so that's kind of the game we're playing here. Now, why might these be useful? Well, we would have to find something that works the way these work. I'll kind of show you what I mean by this, right? if we have a positive number and we multiply it by something now, well, there's three possibilities. Multiply it by x. We might get a positive number, if x is a positive number. We might get 0, if x is 0. Or we might get a negative number, if this is a negative number. Similarly, if I have a negative number, I multiply it by x, I might get a negative number. This is positive. I might get 0 if this is 0. I might get a positive number. It's another negative number. So if I have some positive number and I'm multiplying it by some x, we have the possibility of this cycle here. We multiply it once and we get a negative. We multiply it again, we get a positive. And it continues. We multiply it again, we get a negative. It's kind of, they're kind of two items in this cycle. We get back to a positive, we take 2 turns. That's just how numbers work. I realize this is, like what I'm saying sounds a little, it's either too obvious or it's just peculiar. All right, so now I'm going to introduce this idea of what we call an imaginary number. We can just use I for the moment. And we're going to have a new kind of cycle. It's going to go like this. We're going to take P and we're going to multiply it by something, and we're going to get some new kind of number. We're going to take that number, multiply it again by something, and we're going to get a negative number. We're going to multiply this again, and again we're going to have one of these unusual imaginary numbers. And finally, we're going to go back and we're going to get a positive. That is, we have a cycle here, but instead of getting through the cycle in 2 steps, we get through it in 4 steps. Now, you don't have to really know any of this to know how to work with imaginary numbers. But I bring this up because this comes up in the real world. Here are 2 examples. I don't think we have any electrical engineers. But it turns out that if you're an electrical engineer, you're interested in something called an AC circuit. Everybody knows what AC is, alternating current. Electrical engineer might kind of draw an AC source like this. And electrical engineers like to run AC circuits through what's called a resistor and capacitor. And they like to solve this circuit, meaning they want to know, what the voltage is here, how the voltage is changing, how the current is changing. And it turns out that to solve this problem, you need to use these imaginary numbers. That's one example. Another example is if you're interested in physics and the fundamental nature of what things are made of. Everybody probably knows there's I'm going to draw a little circle. P meaning proton and E meaning electron. And you might know that protons have a positive charge and electrons have an electrical charge. And you might have heard that electrons kind of travel around the proton, and that's what we call, right? Or this is what we call a hydrogen atom, the simplest atom. Well, up to a certain point, like if you're a chemist, that's probably all you need to know. But if you start asking yourself, as physicists do, what are these things? How do they work? You get some funny answers. Like, an electron isn't like the moon going around the Earth, or the Earth going around the sun. It's just, you've got a proton here, and you've got, it's kind of like a cloud. It's kind of a mathematical cloud. It's not a real cloud. There's nothing physically there. But if you say, where's the electron? It's like, oh, it's here, here, right? And the denser the cloud is, the more likely you're going to find the electron there. The cloud is out here, but it's very, very thin. It's unlikely you're going to find it here. You're going to find it close to the proton. And the funny thing is that, physics tells us that this is how to figure out where the electron is. But it's not just a calculation. It seems to be how it really is. It's like the electron doesn't really seem to have a place until you ask where it is. Ask where it is. It's just, well, probably over here where this cloud is dense. So we have this idea in physics. There's this thing called it's called a wave function. It is a function, just kind of like what we've been talking about, functions. But the function is tells us about this cloud. And if you ask the wave function certain questions like, where is the electron? It tells you. It knows everything about that there is to know about the electron. Well, it turns out that for this mathematics to work, this wave function has to be complex, which means we don't really know what that is. It's got imaginary numbers in it, numbers whose square root is -1. It's numbers that can work this way. Instead of going directly from positive to negative, there's kind of an intermediate stage it can go through. All right, now, in all honesty, you don't have to know any of this stuff, right? What you need to know is this, and how to work with imaginary numbers, which is what I'm going to show you next. And that's really what, if I just showed you how they work, you'd be like, what? These are crazy. But these, imaginary is kind of a bad name for these things, because it makes it sound like, well, they're not real. Well, as I mentioned, just regular numbers aren't really real either. They're useful. These imaginary numbers are useful. Let's see how you work with imaginary numbers. Okay, so let's just start with an equation. So who can tell me what the solution to this equation, x squared equals 4?
2 squared.
Well, 2. Yeah, okay. Square 2, you get 4. Is that the only solution to this equation? Okay. Yes?
-2.
Negative 2. All right. Well, notice that the degree of this equation, or the degree of the polynomial, I say x squared minus 4 equals 0, the degree of this is 2, and we have 2 solutions. That's not a coincidence. In fact, we have a very bravado name to describe that. It's called the fundamental theorem of algebra. Wow, we're learning algebra, and this is the fundamental theorem. Says you have a polynomial equation of degree n, it's going to have n solutions. Except, until now, if I wrote this, you'd say, well, you'd say this doesn't have a solution. Well, now we have a solution. We have 2 solutions here. We have 2i, negative 2i. Let's just check those. 2i times 2i is 2 times 2 times I times I. 2 times 2 is 4, and I is negative 1. So that's a solution. Similarly, minus 2i times minus 2i is also negative 2 times negative 2 times I is also negative 4. So you need these numbers for this theorem to be true. Now, you actually we need just a little bit more, because I haven't been mixing these types of numbers and these types of numbers up. So we're not really inventing something new, but we have what we call a complex number. Complex number has the form a plus b times I, where a and b are real numbers. So it's kind of a mixture of real numbers and imaginary numbers. And all real numbers are complex numbers, because b could be 0. And all what we would call a pure imaginary number, like I or 5i or 3.7i, they're complex numbers because a can be 0. And if we have complex numbers, this theorem of algebra we know to be true. All right. Let's talk a little bit more about mechanics. Let's say I say, I have this number here. It's the square root of negative 36, and I want you to simplify it. Well, you just need to take what you know about, quick pause here. Someone here is missing out. Is everybody else has their exam? Well, we can use our laws of radicals. We have to be careful with them. But this is the square root of minus 1 times the square root of 36. Square root of 36 we know, right? That's 6. And this is I. So this is 6i. Now what about adding these numbers? Well, say we have the square root of minus 9 plus the square root of minus 49. Well, we can pull the same trick with each of these. This is the square root of negative 1. Make that more clearly. Square root of negative 1 times the square root of 9 plus the square root of negative 1 times the square root of 49. Well, that's 3, and that's I. It's 3I. This is square root of 49 is 7 times I. And 3 plus 7. Oh, I can treat this I a little the way I treat an x when I'm adding polynomials. 3I plus 7I is, of course, 10I. That's also true for complex numbers. If I have 5 plus 6I and 3 plus 2I, and I want to add these, I just add their real parts, that's 8, and their imaginary parts. You get a complex number. So that's for adding numbers. For multiplying, well, all right, let's see. I had, say, the square root of 5 times the square root of minus 5 times the square root of minus 4. Now here's the one place you have to be careful. I'm going to do this calculation twice, and the second time I'm going to do it wrong, just to show you what you can't do. This is square root of 5 times I times the square root of 4 times I. The square root of 5 times the square root of 4 is the square root of 20. I times I is negative 1. So this is negative, let me make that clear, negative square root of 20. Here's what you can't do. You can't say square root of negative 5 times square root of, all right, I know, according to my rules of radicals, that's negative 5, square root of negative 5 times square root of negative 4, that's the square root of, 20. Wait, that's different. You can't do this. You have to be careful, right? When you're dealing with imaginary numbers, if you've got a radical that's imaginary times a radical that's just imaginary, when you multiply them together, the negatives go away, but you don't end up with a positive, you end up, oh, I didn't write it here. I said that wrong. You multiply two imaginaries, you end up with minus 1. You have minus 20. So that's the one hiccup you have to look out for. Let's take a look at now multiplying well, I guess if we have an imaginary number like, say, 3i, and we multiply it by a real number, times 4, that's no big deal. Again, we just treat this I as if it was like the x in a polynomial. 3 times 4 is 12, and we get 12i. But if instead we're dealing with two complex numbers, things get a little more complicated. It's a little more complex because say I want to multiply 1 plus 2i times 2 plus 3i. Here we're going to find our idea of FOIL useful. All right, everybody want to follow me on this carefully. The firsts are 1 times 2, that's 2. The outer is 1 times 3i, is 3i. The inner is 2i times 2, that's 4i. And the last are 2 times 3, I times I squared, 6i squared. Well, I squared is just I times I, and we know that's minus 1. So this is 2 plus 3i plus 4i plus minus 6. Well, I can combine these now, get minus 4 plus 7i. You can see if you multiply two complex numbers together, you get a complex number. Now, there's circumstances where the number you get, I mean, it would be a complex number, but it might be simpler than this. I'll show you an example of that. I take 2 plus 3i and multiply it by 2 minus 3i. See what happens. 2 times 2 is 4. 3i times 2 is 6i. Outer minus 3i times 2 is minus 6i. And 3i times 3i with a minus. That's 9i squared. So I get 4. 6i minus 6i, that goes away. I squared is minus 1, but I've got a minus here, so it's plus. Yes, question?
Just kind of confused, why is it 6i, minus 6i? Like, shouldn't it be positive if you're multiplying 3i to 2? Oh wait, never mind, I see.
You see it?
Yeah.
Okay.
Never mind.
This one's the positive 6.
Yeah.
This is the minus 6. Well, now this sounds useful. We multiplied two complex numbers and we ended up with something simpler. This is so important that we give this a name. This number here we call the complex conjugate of this number. That is, we have a number a plus bi, and we take the number a minus bi. B can be negative, we just have to make it positive, right? Now we can multiply these two together and we can end up with just a pure real number. In this case, remember your pattern a plus b times a minus b. Well, that's a squared minus b squared. But here, it's not b, it's bi. But when we square I here, we get a negative. So this actually becomes a squared plus b squared. Oh, wow. And that's a real number. That's going to come in really handy. All right. What's this class go to? 3:30.
3:30.
Good. Okay. All right. So, because I want to get to something good, I'm gonna summarize. We want to add two complex numbers. You just add the real parts and the imaginary parts. If you want to subtract, two complex numbers. You subtract the real parts. Did I get that right? No. I'm sorry. Subtract real parts, and you subtract the imaginary parts. If you want to multiply, two complex numbers, so you separate these two. Add, subtract, multiply. We're going to use FOIL, and we're going to do it carefully. We have AC. We're going to multiply B and D, but the I squared is going to be minus, so it's going to be minus BD, and that's our real part. And then we're going to have BC and DA. We're going to do this with numbers, so it's not so abstract. And that's going to be our imaginary part. So that only leaves division. We don't know how to divide yet. So what if I was going to divide A plus BI, C plus DI? Well, it turns out that the trick is to remember our complex conjugate. Watch, you know, nothing up my sleeves, right? It's like a magic trick here. I'm going to multiply the bottom by the complex conjugate of the bottom. But I also have to multiply the top. These two are going to give me a real number. And I already know how to multiply the top. So let's do a real example here. See how this works. Let's say 2 plus 3i divided by 1 minus 4i. Well, my complex conjugate is 1 plus 4i. Let's change the sign on the imaginary part. Multiply the top by 1 plus 4i. And the bottom, I'm always going to get a squared plus b squared. In this case, 1 plus 1 squared plus 4 squared. It's going to be 16 plus 1 or 17. I think I did that too quick. I'm going to try it again. The first, 1 times 1. The last, 4 times 4i minus. So minus 16. And then my inner and outer, because they're complex conjugates, are going to drop out. So I get 17. Now on the top, okay, I have to do FOIL. 2 times 1 is 2. 3i times 4i is 12i squared minus 12. I get my 3i and my 8i. Okay, so I've got minus 10 plus 11i over 17, which really means I have minus 10 17ths plus, this was not a good example because these numbers are ugly, but here again I have a complex number. So I can add, subtract, multiply, and divide these numbers just like any other kind of number. It's just a little more work. Okay. Do I have time for fun? Yes, I did. I guess I gotta get this thing going. in my lifetime, a very famous mathematician by the name of, I don't know his first name. Oh, his first name is Benoit. It sounds French. Benoit Mandelbrot. He was a mathematician. He worked at IBM. He was theoretical, though. They just hired people to do stuff. And he came up with this idea. We're going to plot, we have a real number line here. He didn't come up with this part. We plot the imaginaries like this, kind of like x and y. And so every complex number has a point on here. Like this is 1, and this is 1, and this is 1 plus r. Then he said, okay, let's take these numbers, let's take a number here, and start multiplying it by itself. Whatever number it is, 2 plus 3i, whatever, 0.5 plus 1/2 plus 1/3 I. We take all these points and we multiply them by themselves. And we see what happens. Now, one of two things is going to happen. If these are small numbers, they're going to kind of stay around the origin here. They're small, and they're going to just stay there. If they're big, they're just going to fly off. They're going to get larger and larger and larger. Just like 4 times 4 times 4 times 4, it gets very large quickly. But it turns out that around the periphery, they're numbers that they're kind of vague what they do. They don't just stay here. They don't go flying off. They just kind of float around a little, and then maybe they fly off or maybe they come in. We don't know. Now, if you take this idea, if you graph the ones that stay near, we call that the Mandelbrot Set, after Benoit. But with the advent of computers, we could do this for a lot of points, and we could represent this using color. So, I have to log in. Password is very difficult. Okay, so you can find this kind of stuff on the web. Here, the black area is what we call the Mandelbrot set. The red is outside of it, but you notice close near the edge, it kind of gets kind of fuzzy. It's colored, certainly. With this viewer, you can kind of pull in, start looking at some of the detail. Now, one of the things you might have noticed is there's these little blobby things that kind of are shaped like the Mandelbrot set within it. They're part of it. And you can get closer, and you can get closer, and you can get closer. It keeps going. And that brings me back to that video I was showing earlier. Start it over. It's just amazing. Not only complicated, complex. It's really beautiful. We're going to zoom to 10 to the 99th. Oh, I guess I have to. Make it a little dark. And this is computer generated. And you can see we just keep going, more and more detail, finer and finer. It got boring for a little while, but there's more stuff here, there's more stuff here. It's like, this is not something somebody invented. This is something that was already there out in abstract math land before we were born, and it's just kind of amazing. You will not be tested on this, of course. It's here for your entertainment. But I just wanted you to know that, you know, this really kind of wacky idea that doesn't seem to make sense at first, square root of -1, it opens up this whole world of curious kind of things. The technical name for this object is called a fractal. Fractals in math are things where they look the same at all different scales. Right? No matter how much we, you know, zoom in, we see things that look very similar. Like, well, there's one going by there. Okay, that's really it for today. I hope you enjoyed the video part. Hope this will give you some enthusiasm about this homework assignment where you're going to do stuff with complex numbers, learn a little bit about manipulation.